so far we have seen simple functions, measurable functions, and we have defined integrals for positive simple functions, and taking appropriate supremum we defined integrals of positive measurable functions, and we looked at some properties like monotonicity and things like that. And if you integrate over a set of measure 0, you will get 0 even if the function is infinity at that set, and if the function is 0 you integrate, you will get 0 even if the set has infinite measure. So today we will prove one or two important theorems in integration which will allow us to interchange the integrals and limits very easily. So this is one of the advantages of Lebesgue's theory of integration over Riemann integration. In Riemann integration we needed a sequence of functions to converge uniformly for us to interchange the limit and integral. That is not necessary in the case of Lebesgue integral. So we will see that today. So the first theorem we want to prove is Lebesgue's monotone convergence theorem. Monotone convergence theorem. So we will call this MCT for monotone convergence theorem. So let me write this in full detail. So as usual we have a triple X F mu. X is any space, F is a sigma algebra of subsets of X, mu is a countable additive measure. Okay. So let Fn be a sequence of non-negative measurable functions defined on X such that Fn's are increasing. That means F1 is less than or equal to F2, less than or equal to F3, etc. So Fn's actually increase. So Fn of X at each X would be an increasing sequence of positive numbers. So they will have to converge. They may go to infinity, but they will converge to something. So let us call the limiting function F. So let F of X to be equal to limit n going to infinity Fn of X for every X in X. So this of course exists because Fn's are increasing, and then F is of course measurable. Then F is measurable. It is a limit of measurable function, so that is not surprising. But what is interesting is that we have limit of n going to infinity integral of X Fn d mu. So remember these are all well defined now because Fn's are non-negative measurable functions. We know how to define the integral of Fn with respect to a measure. This is actually equal to integral of X F d mu. So to remark, we are interchanging limits and integrations. Okay. So this is interchanging limit and integration, right, because we are saying limit of n going to infinity integral over X Fn d mu. This is actually equal to integral over X limit n going to infinity Fn. So that is our F, right, and d mu. So we are saying this can be done if you have a sequence of increasing measurable functions, okay, non-negative increasing measurable functions. So proof. So this is one of the most useful theorems you will see in measure theory. We have three such theorems which will allow us to interchange limits and integration. We will see one more today, and then when we define integration for real valued and complex valued functions, the third theorem will come. Okay, so let us define again f of x to be equal to limit n going to infinity Fn x, right. So this is for every x in x. So then f is measurable. Then f is measurable because it is the limit of measurable functions. Limit of measurable functions is measurable. Okay. we want to compute the integral of f and see if it is the limit of integral of fn's. Okay. Now what do we know? We know that fn's are increasing. So fn is less than or equal to fn plus 1, less than or equal to fn plus 2, etc. Because of the monotonicity property of the integral, we have integral over x fn d mu is less than or equal to integral over x fn plus 1 d mu. So if you look at the sequence of positive numbers, so remember fn's are non-negative measurable functions and I am integrating over x with respect to a positive measure. So I am getting these are all positive numbers. Sometimes they can be infinity, but let us not worry too much about it. We have a sequence of positive numbers, let us call that an. What we know is an is less than or equal to an plus 1. So an is an increasing sequence of positive real numbers. So it will converge, it may go to infinity or some finite number, let us say a. Now what do we know? We also have fn to be less than or equal to f for every n, right, because f is the limit of the increasing sequence of fn. So for each n fn is less than or equal to f, and so integral of x fn d mu will also be less than or equal to integral of x f d mu for every n. But this is a sequence which converges to a. So a is less than or equal to integral of x f d mu. So this is one inequality, right. So what we are proving is that limit of n going to infinity integral over x fn d mu, that is my a, that is less than or equal to integral over x f d mu. Okay, this much did not use anything too difficult. Only thing we needed was the monotonicity of the integral and the fact that these numbers an's were increasing, and so we got an increasing to a. Okay, so now let us prove the other way. Suppose 0 less than or equal to s less than or equal to f and s is a simple function. So recall that we defined integral of f, so that is something let us recall immediately. Recall integral of a non-negative function f is the supremum over all the simple functions less than or equal to f integral of x s d mu, right. So s d mu is something which we know. We know how to define this using the measure and the expression for s, and we take supremum over such things, we get integral of f. So I am going to use that now. So take any simple function which is between 0 and f. Let us fix a number c less than strictly less than 1, okay, and define the following set En. This is equal to all those points in the space x such that fn x is greater than or equal to c times s of x. So remember, s is a simple function less than or equal to f, c is something which is less than or equal to 1. So c times s is something strictly less than f, and I am looking at all those x such that fn x will be greater than or equal to c times s of x. So it is easy to see that En increases to the whole space x. Well, why is that? So let's justify this. If I take any x in x, I know that fn x increases to f of x, right. For at each x we know this happens. But if I look at c times s of x, this I know is strictly less than f of x. So there exists some n naught such that c times s of x will be less than or equal to fn naught of x less than or equal to f of x, right, because fn's converge to f. So it has to be between this number and this number as n becomes bigger and bigger. and so that particular x will be in En naught. And so, well, because Fn's are increasing, En's are increasing. So, this simply tells me that union of En is the whole space n equal to 1 to infinity. Moreover, it increases, right. So, E1 is smaller than E2, smaller than E3 and so on. Okay. So, well, how do we use this? We start with integral over x Fn d mu. Remember, these are positive numbers, increasing, we know it converges. We need to show that it actually converges to integral of f. Well, this is of course less than or equal to, sorry, greater than or equal to integral over En Fn d mu. Recall that integral over En Fn d mu is integral over the whole space x, indicator of En times f. So, let's recall that part. So, right, integral over En Fn d mu, we know by definition this is integral over x, indicator of En Fn d mu, which is of course less than or equal to integral over x Fn d mu, right, because chi En is less than or equal to 1. So, I can, by monotonicity of the integral, I can do that. That is how we get this, right. This is of course greater than or equal to, well, on En we have an inequality, right. So, we can use that. Using monotonicity of the integral again, we get the constant c that will come out of the integral over En s d mu, right, because s c times s is smaller than Fn on the set En. So, we use the monotonicity of the integral again there. Okay. So, now we are in good shape because the right hand side now, well, what will happen to this? So, let's write down this again. I have integral over x Fn d mu to be greater than or equal to c times integral over En s d mu. Okay. So, let us recall the result we proved in the last class. So, we proved that if s is non-negative and simple, then if I define nu of a to be equal to integral over a s d mu, then nu is a measure. We proved that. Okay. So, this is a measure, and En's increase to the whole space, En's increase to whole space. Okay. So, nu of En, we know by the property of the measure, will have to increase to nu of x. So, this increases as n goes to infinity to c times integral over x s d mu. But for each n, I know this is bounded by integral over x Fn d mu, right. So, this is of course less than or equal to, sorry, let's put this. So, I know that this goes to our number a, right. This is what we called a. Let us see if it is here. Yes. So, the a is simply the limit of these integrals. So, this goes to a. So, what we have is a greater than or equal to c times. So, let's write that separately so that it is clear. So, let us recall a is simply limit of n going to infinity integral x Fn d mu. What we have just proved is that a is greater than or equal to c times integral over x s d mu. So, what was c? C was less than 1, some fixed constant. What was s? S was less than or equal to f. So, this is true for all c and all s like this, right. Any c between 0 and 1, any s between 0 and f, we have this inequality. Left hand side is independent of everything. So, I can take supremum over c and supremum over s less than or equal to f, and I will, on the right hand side, I will get the integral of f. So, this implies that a, which is the limit, of Fn's Fn d mu I know is greater than or equal to integral over x f d mu, right. So, this is one inequality, and the other way inequality was the easy part which we did, right, which uses only the monotonicity. So, we had this inequality. So, limit of fn's to be less than or equal to integral of f, and now we have limit of fn's to be greater than or equal to integral of f. So, this tells me that limit of n going to infinity x f n d mu is actually equal to integral of x f d mu. Okay. So, this is the monotone convergence theorem. If you have increasing sequence of measurable functions, then you have convergence in the integral. Okay. That is what monotone convergence theorem tells you, but you have seen so let me remark, you have already seen an instance of this when we started with a measure. So, recall, suppose I have a measure mu, and if I have sequence of measurable sets A1 smaller than A2 contained in A3, etc., right. So, this is what we call An increasing. N increases to A. What is the A? What is A? That is the union Aj j equal to 1 to infinity. In this case, you know that mu of An increases to mu of A. This was a property, countable additivity property of mu. Well, now this is part of the monotone convergence theorem, because what is mu An? We are looking at chi An. I know An increases to A, so chi An will increase to chi A, and by MCT, the monotone convergence theorem, we know that integral of chi An d mu will increase to integral over chi A d mu, right, over the whole space x, which is same as saying mu of An increases to mu of A. So, you have seen an instance of the monotone convergence theorem for indicator functions. Okay. So, this is a much more general theorem which is applicable to all positive measurable functions. So, there are immediate corollaries to this which are very useful, and you will also see something which you have probably seen earlier. So, corollary. So, again we have this triple, and let us say we have a sequence of measurable functions 0 to infinity measurable. Okay. Define f of x equal to summation fn of x n equal to 1 to infinity. So, I am adding positive numbers. So, it will exist, it may be finite or it may be infinite. Okay. Then f is measurable, and the more important part is integral of f d mu is the sum of integrals of fn's. Okay. So, let's corollary 1, let us prove this. So, positive part is important, otherwise there are things that can go wrong. One has to be careful about convergence and so on. Well, so how does one prove this? So, let us start with the simpler case. Suppose I have two functions, suppose f1, f2 non-negative measurable functions, negative measurable functions. Then I know that there are sequence of, so there exists sequence of non-negative simple functions. So, we will call them Sj1 and Sj2. Okay. Sj1 will converge to f1, Sj2 converges to f2. So, we know this for any non-negative measurable function, I know there is a sequence of simple functions increasing to that function. But now by monotone convergence theorem, I know that integral of Sj1 d mu will increase to integral over f1 d mu, and integral of Sj2 d mu, the second sequence, will converge to the second function. So, we know this by MCT. Okay. But for simple functions we already know linearity. So, remember that. So, we proved that. So, let us recall that if S and T are simple, then we know that integral of s plus t d mu equal to integral over x s d mu plus integral over x t d mu. We did this in the last class for simple functions. So, we use that. So, if I look at integral over x sj1 plus sj2 d mu, I know that this is equal to integral over x sj1 d mu plus integral over x sj2 d mu. So, we can use monotone convergence theorem again, right, because sj1 plus sj2 will increase to f1 plus f2. So, by MCT we have integral over x sj1 plus integral over sj2 d mu will increase to integral over x f1 plus f2. This is by MCT, but I know that this is equal to, because it is linear on simple functions, this is simply the sum of two things plus integral over x sj2 d mu, and I know that this increases to integral over x f1 d mu plus integral over x f2 d mu. So, remember we started, this also converges to this. So, we have, what we have proved is that linearity of integral over positive functions. So, whenever you have positive functions measurable, you can add them up. So, of course, if you have three functions, you will get three pieces and so on, right. Finitely many functions, you can always do this. So, now let us get back to the proof of this. So, we are looking at countably many measurable, positive measurable functions. We are looking at f of x equal to the sum of these things, and we want to say, we want to prove this, right. This is what we want to prove. Okay. So, we use monotone convergence theorem again. Okay. So, we use monotone convergence theorem again. Okay. So, recall we have f1, f2, f3 etc., right. This is what we called f. So, let us take the partial sums. So, let us call that gn of x to be f1x plus f2x plus f3x plus etc. plus fnx, right. Then what we know is fj's are all positive. So, gn's are increasing, right. Where will they increase to? They will increase to the whole sum, which is f. So, gn's increase to f. So, by MCT we will have integral of gn d mu will increase to integral over x f d mu. But what is this? Gn is a finite sum. We just proved that if I have two functions, I know how to the linearity of the integral over two functions we know. So, similarly for finite sum we have the same result. So, this one would be simply summation j equal to 1 to capital N integral over x f j d mu, right. But as n goes to infinity, what will happen to this? So, as n goes to infinity, this goes to the sum j equal to 1 to infinity integral over x f j d mu, right. So, this and this will have to be same. So, that is what precisely our statement of the proof, statement of the theorem, right. If I have f to be the sum of fn's, then the integral of f is the sum of the integral of fn's, right. Remember, they are all positive measurable functions. When you apply monotone convergence theorem, you have to be careful. You apply it to increasing sequence of functions. Okay. So, let us look at another corollary. This is something which you have probably seen, when you studied series of positive numbers and so on. Suppose I have numbers aij positive, I equal to 1, 2, 3 etc. Similarly j equal to 1, 2, 3 etc. Okay. Then summation aij j equal to 1 to infinity, summation I equal to 1 to infinity. This is same as summation j equal to 1 to infinity, summation I equal to 1 to infinity aij. So remember we are changing the order of the summation, changing the order of the summation, right. So whenever aij are positive you can do that. So that is a easy consequence of the monotone convergence theorem. So I will leave it as an exercise to you. Well, how do you see this? So this is, remember summation is an integral, right, and we just proved that if I add up functions I can change summation and integrals, right, that is what we proved. So use this result and make sure that your integral over x is the summation. So remember, if you look at natural numbers with counting measure, then each of this can be viewed as an integral, and so you have one summation and an integral and you know how to interchange them using monotone convergence theorem. So use corollary 1, okay, and MCT. Okay. Okay, so the first part we will stop with the following lemma, which is another important result. It is called Fatou's lemma. So as usual we have x f mu and I have fn, again positive measurable functions, measurable, okay. Then integral over x lim_inf of fn d mu, this is less than or equal to lim_inf of integral fn d mu. Okay. So remember these are numbers and I am taking the lim_inf. Here it is the function lim_inf fn. So let us recall that lim_inf fn at x is, well, it is supremum over n, infimum over k greater than or equal to n fkx. Okay. So the proof of this is 2 lines from using MCT. So all we do is we look at this as a collection of functions for each n. So define gn of x to be infimum over k greater than or equal to n. So for each n you fix n and look at all k greater than or equal to n and look at fkx, right. Take the infimum of that. These are positive ones, so you will have an infimum which may be 0, does not matter, but you will have an infimum. Now you are looking at infimum of various things, and as n increases the set you are looking at is smaller and smaller. So the infimum will increase. So GNs are measurable of course, because supremum and infimum of measurable functions are measurable, and GNs are increasing. GN are increasing. So it will converge. Where does it converge to? Gn increases to supremum of GNs, right, because GNs are increasing, but supremum of Gn is precisely the lim_inf of Fn. So Gn increases to lim_inf of Fn. So by MCT, the monotone convergence theorem, integral over x Gn d mu will converge to integral over x lim_inf of Fn. Okay, so let's use one inequality here. So let's call that let's recall that Gn. So remember Gn of x is infimum of k greater than or equal to n fkx, and so this is of course less than or equal to fnx, right, because I am looking at, so what is this? This is infimum of fn x, fn plus 1x, fn plus 2x, etc., etc. So, fnx is one such element, and so infimum will be less than or equal to that. So, this tells me again by monotonicity of the integral, I have integral over x g n d mu to be less than or equal to integral over x f n d mu. I know that this converges to integral over x lim inf of f n d mu, and so of course I can say this is less than or equal to lim inf of integral over x f n d mu, right. These are, so what am I using? If I have a sequence a n, and so this is a simple exercise, a n and b n positive sequences, okay. I know that a n converges to a, or a n increases to a n increases to a, and a n is less than or equal to b n, okay. So, this implies a is less than or equal to lim inf of b n, okay. That is all we are using here. So, this is called Fatou's lemma. So, Fatou's lemma is an inequality, it is called Fatou's Illy lemma. Integral lim inf is less than or equal to lim inf of integrals. This is another extremely useful result. So, you have just seen two results where interchanging of the integral and limits are interchanging of the limits and integrals are involved. First is the monotone convergence theorem, which allows you to interchange the limit and integrals if you have a sequence of increasing measurable functions. Okay. If you have a sequence of positive measurable functions, you have an inequality which is given by Fatou's lemma. Okay. So far we have seen monotone convergence theorem and Fatou's lemma, which allows us to interchange integrals and limits. In the next session, we will look at complex valued functions and how to integrate them. So far we have integrated only positive functions. Starting from positive simple functions, we have gone to positive functions. We know the integral is linear there. Now we will extend it to real valued functions and then to complex valued functions, and then one more result of this kind which will allow us to interchange limits and integrals will be proved.